Hello learners, my name is Ms. Vinita Janardhan Rao, Assistant Professor in Mathematics from Ganpat Pasikar College of Education. I welcome you to Module 4 of Elementary Combinatorics, which is Strong and Weak Induction Part 2. In this module, we will be learning about strong induction principle and few examples based on it. Strong induction principle, again we have two steps over here, that is the initial step and the induction step, like we have seen in the weak induction principle. But in addition to that induction step of weak induction principle, we have something more to it. Let us go through it. The initial step is we prove that the statement is true for the smallest value of m for which it is defined, usually 0 or 1. The induction step proves that from the fact that the statement is true for all integers less than n plus 1. So this is important over here. For all the integers less than n plus 1. So basically we are talking about all the integers which are less than or equal to n. We assume that the result is true and we are trying to prove the statement for n plus 1. First example, let the sequence an be defined by the relations a0 equal to 0, that is the first term is 0, and an plus 1 is expressed in this form, a0 plus a1 up to an plus n plus 1 if n is greater than or equal to 1. Prove that for all positive integers n, the equality an is equal to 2 raised to n minus 1. If we see over here, this n plus 1th term, it is not only dependent on the previous term an, but also it depends on a0, a1 and so on. So here weak induction principle is not applicable. We have to make use of strong induction principle. We'll prove the initial step for n equal to 1. So when we say n equal to 1, we get over here, or instead of taking n equal to 1, we can easily prove n equal to 0. n equal to 0, it is simply a0 which is equal to 0 already given to us. So it is of the form 2 raised to 0 minus 1. Okay, 2 raised to 0 is 1, 1 minus 1 is 0. So this implies that the result is true for n equal to 0. We have to prove only one, either 0 or equal to 1. If we try for n equal to 1, we will get over here for a1, we should be able to express it as 2 raised to 1 minus 1. So in this case, if you put n equal to 0, we will get 0 plus 1, which is a0 plus 0 plus 1. Put n equal to 0 in that expression. a0 is nothing but 0, so we will finally get value 1, which is 2 raised to 1 minus 1. So we see that the result is true for n equal to 1 as well. Next, we assume that the result is true for all the positive integers which are less than or equal to n. So assume the result to be true for all the integers less than or equal to n. Then what do we get? So then our recurrence relation an plus 1, which is equal to a0 plus a1 up to an plus n plus 1. Okay. So from here, by taking help of this assumption, we will try to prove that the result is true for n plus 1, meaning we have to show that a n plus 1 is equal to 2 raised to n plus 1 minus 1. Now we know that the result is true for all the integers less than or equal to n. That means a naught is of the form 2 raised to n minus 1, that is 2 raised to 0 minus 1, plus a1 is 2 raised to 1 minus 1 up to an is 2 raised to n minus 1 plus n plus 1. Next what we'll do is we'll combine these terms which are of the form 2 raised to something. So it is 2 raised to 0 plus 2 raised to 1 up to 2 raised to n plus, now here we see minus 1 up to minus 1 which are appearing n plus 1 times because these are n plus 1 terms. So this will be minus of n plus 1 plus n plus 1. So here we'll see that these two terms will get cancelled and we'll be left with 2 raised to 0 which is 1 plus 2 up to 2 raised to n. Now if we compute this particular sum, value of the sum will be a into r raised to the number of terms minus 1 upon r minus 1, wherein r is the common ratio. So first term is 1, common ratio is 2 raised to the number of terms which is n plus 1 minus 1 upon r minus 1. Hence the value is 2 raised to n plus 1 minus 1. So we see that in this case we have proved a n plus 1 is 2 raised to n plus 1 minus 1. Therefore, the result is true for n plus 1, and hence by strong induction the result is true for all positive integers. Let us look at the next example. Let f from n to n, that is set of natural numbers to natural numbers, be a function satisfying f of n plus m is equal to f of n plus f of m for all m and n. Prove that there exists a constant c so that f of n is equal to c times n. Here let us try to prove this by the method of strong induction. So we'll first prove the result for n equal to 0. Now if we have to prove the result for n equal to 0, that means f of 0 should be equal to some c times 0. Now for that we'll take help of this expression, the way your function is defined. If we consider m equal to 0, we'll get f of n plus 0 equal to f of n plus f of 0. So this implies f of n equals f of n plus f of 0. That means f of 0 will be equal to 0, which is of the form, if we take any constant c and multiply it to 0, it is again giving us value 0. So f of 0 is same as c times 0. So therefore the result is true for n equal to 0. Now let us assume the result true for all natural numbers less than or equal to n. That is, there exists a constant c such that f of k is equal to c times k for k is less than or equal to n. Now we have to prove the result for n plus 1. Now in particular, f of 1 is nothing but c times 1, which is c. So for k equal to 1, which is less than or equal to n, f of 1 is nothing but c. And since the result is true for the value n, f of n is equal to c times n. Here we are substituting k equal to n. This implies f of n plus 1 is nothing but, so in place of m we have to put 1. It will give us f of n plus f of 1, which is equal to, let us substitute f of n as c times n plus f of 1 as c. Now take c out, it will be c times n plus 1. So what do we see over here? That f of n plus 1 is equal to c times n plus 1. So therefore the statement is true for n plus 1, and therefore by strong induction principle the result is true for all m and n, which are your natural numbers. This is the reference book you can follow, which is a walk through combinatorics. Thank you.